let's talk about the infinite square well, the 1D infinite square well, and non-stationary states. So I've already done the derivation in many different ways of Schrodinger's equation, which is this right here, for an infinite square well. So a length a with infinite walls, so the function can only exist in here, the wave function only exists here. And this is a wave function of space and time. What we did for the solution to solve this problem was to assume that we can break this into a space part. Actually, I should write this like this. Psi of x and t is equal to some time part, which we can solve for quite easily. I'm not going to redo it. E to the negative I, technically E n t over h bar psi of x. And in this situation, I'd have these psi's represented by the sine function in pi x over a. I'd have to normalize it with this constant a, square root of 2 over a, where that's the length. And then you get the energy values that are proportional to n squared. And that's fine. And so what happens is, if I have one value of n, if I plug this back in up here, it works. And if I want to find the probability distribution, P is psi star psi, what happens is that I get the complex conjugate of this is I e to the nt over h bar times the normal value with the negative, and those two things cancel and become 1. So you get no time dependence. And that's why we call this we would get psi star psi, and this is, let's say for the first energy, 1, 1. And this is called a stationary state, because it does not have any time dependence. If you put the wave function in like that, it just stays right there. It doesn't do anything. But what if I have multiple energies as my wave function, or I have some different wave function to start off with? Then it does change with time. And that's what I want to show you. But basically what we can do is to say, if I have this psi 1, let's say psi 1 uses n1 and psi 1 right here, this capital psi 1. And that's a solution to this differential equation. And psi 2 is the different solution to the differential equation. Then psi equals psi 1 plus psi 2 has to be a solution to the differential equation. Because when I take the derivatives, I'm going to have essentially psi 1 in here, psi 2 in there, and then it'll still work out. And you can try that if you want. So let's try using the following. Let's suppose that I have the energy level n1 and n2. So psi 1 as a function of x and t is some constant c1 e to the minus I e1 t over h bar psi 1. And psi 1 would be a sine omega t. That's fine. Sine, yeah. It's just the sine thing. And we'll plug that in later. But let's just leave that as psi right now. And then I have psi 2. Let's just say I have my total function plus c2 e to the minus I e2 t over h bar psi 2. Now let's say I want to, and I'm assuming here that these are real values. Real, they don't have any complex numbers in there, and that's fine. Now let's find the probability. P is psi star psi. So I need to take the complex conjugate of this and multiply it by the normal thing. So if I take the complex conjugate of this, I'm going to replace the i's with a minus I. That becomes c1 e to the I e1 t over h bar psi 1 plus psi 2 e to the I e2 t over h bar psi 2. And then I need to multiply by the original c1 e to the minus I e1 t over h bar psi 1 plus c2 e to the minus I e2 t over h bar psi 2. And that looks messy, and it's a little messy, but it's handleable. So let's just multiply this out. I'm going to take this times that. That's pretty easy. I get c1 times C1 squared. I get this times that. And here I have I E1t over h bar and minus I E1t over h bar. So these two multiply give us this 1, and then psi 1 times psi 1 is just psi 1 squared. Now let's do this one because it's easier. This times this is going to be the same thing, plus C2 squared, psi 2 squared, because this has an E2 and an E2. So when I multiply these two together, they give me 1. That's nice. Now for this term. This times this term will be plus C1, C2, psi 1, psi 2. Now I'm going to get this times this. And I'm going to write this as e to the minus I E2 minus E1 t over h bar. Because here if I'm adding these two exponents, I'm going to factor out the minus I. If I factor out the minus I here, that becomes negative. And so I get E2 minus E1. Everything else is the same. Now I got to do this term times that. And I get the same thing, but opposite, right? Because now E2 has a negative sign. So I'm just going to write this as, factor that out, plus e to the I E2 minus E1 t over h bar, right? Because if I take this times this, I'm going to keep the E2 in the front. I want it to be E2 minus E1. So I'm just going to add these two terms. I'm not going to force it. I'm going to bring that negative sign in there, and I get a plus. And there's a reason to do that, as you might expect. Let's make a variable change. I'm going to say theta is equal to this thing inside, E2 minus E1 t over h bar. Then this stuff right here becomes e to the minus I theta plus e to the I theta. This is very useful because I can now use the Euler formula. And yes, there are 50 bajillion Euler formulas, but this is one of them. It says that e to the I theta is equal to cosine theta plus I sine theta. So this right here, let's write that. If I bring the minus into the theta, e to the minus I theta is cosine of minus theta plus I times sine of minus theta. And you'll notice that cosine of minus theta is the same as cosine of theta. And sine of minus theta is minus sine of theta. That means that if I add these two together, e to the minus I theta plus e to the I theta, I get two of these, 2 cosine theta, and then these two are going to cancel. And so I got rid of the exponential, the imaginary numbers. That's kind of yay. And now I can put back this in. So overall, I get the following. Psi star psi is going to be equal to C1 squared psi 1 squared plus C2 squared psi 2 squared plus C1 C2 psi 1 psi 2. And then I have 2 cosine E2 minus E1 over h bar t. And we're going to plot that. But you'll notice that if I say psi 1 is square root of 2 over a sine of n pi x over a, which is just going to be pi x over a, and psi 2 is square root of 2 over a sine of 2 pi x over a, and I have different energies, right? I have E1 is going to be n, which is 1 pi squared. What was it? I always forget that energy for some reason. Pi squared h bar squared, pi squared h bar squared over 2ma. And E2 is 4 pi squared h bar squared over 2ma. So I have all my values there, right? I can plot this, but it does change with both space and time. But I want to point out one thing. I could write this as omega, or 2 pi f times t. So 2 pi f t equals E2 minus E1 over h bar times t. And h bar is h over 2 pi. So I can write this as equal to 2 pi f t E2 minus E1 t 2 pi over h. Or cancel, delta E equals hf. Does that look familiar to you? And I put the delta in there, right? But we see this and where we talk about the Planck relationship between the frequency of light and the change in energy. And I want to point out that when we talk about the change in energy, we always get that by having light interact with matter, whether that's a detector or something. So that change in E is in the matter. So this is really the matter side, and this is the light side, I like to think of it. But that's not super important. What I want to do is to model this probability density as a function of time. And so we're going to make an animated graph. Of course, we need some numerical values for this. I'm going to use m equals 1, a equals 1, h bar equals 1. I know that's silly. And I do need c1 and c2. c1 let's use as the square root of 3 over 10, so that's normalized. c2 is square root of 7 over 10. And then let's just plot this. So this is going to be some practice making some animated graphs, but it's going to be awesome. And I will give you the code. So I'm switching over here to Python. And this is Web v Python, if you're not familiar with this. It's not real Python, it's fake Python, but it's just as awesome, and it does really make great graphs. So let's just get started. I'm going to go ahead and start by putting my container for my graph. I'm going to plot psi star psi versus position, but it's going to be animated. So G1 is equal, that's not big enough. Bigger, that's good. G1 equals graph, title equals 1D square well. This is fine. X title is X. I'm going to leave off the units. Y title is psi star psi. And then I'm going to give it a width of 400, height of 200. And that just makes it so that it appears fine in my tiny little window here so that you can see it. I need a graph. I'm just going to call it F1. F1 is G-curve. I always like to give it a color, and I use blue. I don't know why I always use blue, but that's that. Okay, so that's that. Now I need my constants. H bar equals 1, M equals 1, A equals 1, C1 equals square root of 3 over 10, C2 equals square root of 7 over 10. And what I'm actually going to do, and I do need time, and I need x. So x equals 0, t equals 0, dx, this gets a little, I'm just going to pick 0.01 and dt of 0.01. I'm plotting an analytical function. I'm not doing a numerical calculation, so it doesn't really matter how big those things are. It should be fine. I'm going to just plot out my stuff at t equals 0, and then we can animate it. And that'll be a good practice for us to get these things to work. So let's start off with the energy levels. E1, I'm going to say E1 is going to be, I could make it a function, but I'm just going to make it. So it's going to be pi squared times h bar squared divided by 2 times m times a. That was right? Yeah. And then E2 is equal to 4 times pi squared times h bar squared divided by 2 times m times a. Okie doke. I think we're ready to go. I'm going to plot my x values from 0 to a. I can do that with while x is less than a. And I'm just going to calculate how should I do this? Let's just calculate the whole thing, the whole function. I'll call it P. P is equal to, I'm just typing in my function. Actually, I'm going to do this. I'm going to calculate psi1, because that's the way I wrote it down. Psi1 is, I need this, let's put this a term in here too. A equals square root of 2 over a. So this is a times sine of n, which is 1, pi times x over a. That's that. Psi2, and it's in the loop, so every time I get there and I change my x value, I'm changing my psi value. Psi2 is a times sine 2 times pi times x over a. Now I can type my p equation. I'm looking at it. It's I have that c1 squared times psi1 squared plus c2 squared times psi2 squared. Now I have my cross term, plus, I'm going to type it out even though I'm putting t equals 0, plus c1 times c2 times psi1 times psi2, so this is where it's nice to have those already calculated, times 2 times cosine e2 minus e1. Ooh, I need another parenthesis, almost messed up there. Times t over h bar. Where's my other parentheses? Did I delete it? Okay, there. That's my p. Now I'm going to plot it, and I'm going to increase x. I'm going to do the whole thing again. So f1 dot plot x p, and then x equals x plus dx. Let's see if it runs. It might not, because you know I make mistakes. Okay, that's it. It did it. It plotted it. But that's at t equals 0. I didn't even, oh, I did put t equals 0. See, because I even had t, and I put t as 0, so it's fine. Okay, now we want to change t and rerun it. To do that, we need to put a loop inside of a loop. Let's run this for 5 seconds. And I don't have real times here, so that's fine. While t is less than 5, colon. And I want to do all this every single time. But to do that, there's a couple things. One, I need to reset my x. At the beginning of the time loop, x equals 0. I need to go back to x equals 0. This will then calculate all the functions, and then I need to update time, t equals t plus dt, or it'll never end. I also need a rate statement, because otherwise it'll just go as fast as it can, and I want to animate it. Now there is one other thing. What I need to do is in order to make an animated graph, I need to take my data points, put them in a list, and then plot them. So every time I don't want to plot every single point, this plots one point and it goes through the loop. I don't want to do that. I want to add it to a list, and once the whole list is done, then plot it. So we can do that with a list called, I'm going to call this f data equals an empty list. And down here, I'm going to add a point to that, f data equals f data plus xp. I'm going to add that data point. Now at the end of my loop, once I get out of my loop, I can now plot the whole thing. f1 dot data equals f data. That's how you do that. Whew. Let's see if it works. I kind of think it won't, because there's a lot there, and I didn't even save the thing. So I should save it. Superposition of energy states. Save. Okay, let's run it. Kind of scared, but you should be a little bit scared. If you're not a little bit scared, you're not pushing yourself. Okay, it's working. Now it doesn't look perfect. I'm going to fix the perfectness, because you'll see that as it oscillates up and down, the maximum psi star psi is not constant, so the graph scales. Let's just put that at 3.5, and I think that should fix it. I can do that up here. Y max equals 3.5, and we're going to have a pretty much textbook quality graph now. Look at that. And so it oscillates between those two states like that. And that's not a stationary state. It's not stationary. If you want to put in, change E1 to E2, then the time thing will cancel and it'll stay stationary. You can have any number of states that you add in there to plot anything, and that's kind of cool, right? I could have C1, C2, C3. I can have different amounts of the three things, and I'll get different results. Now, if I change C1 and C2, it will change the shape of the graph. I don't think it'll be normalized. But the oscillation between these two will stay the same. It'll be the same, right? Because that depends on the change in energy. It doesn't depend on how much. So let's do that just for fun. Let's just say this is C1 is square root of 5 over 10. And I'm going to comment that out. And then let's just change this to 5 over 10. I don't know why I did that. I just did it. Did it change what it looks like? I think it changed what it looks like. Maybe not. Maybe it did. I think you have to check the normalization, and I don't think normalization changes with time, but I'm not going to do that today. We can do that at a later point. You can have it one time, integrate over the thing, and see if it has a value of 1. If not, you can renormalize it. But there's another way to model this non-stationary state with the finite difference calculation, but we'll do that later. So I'll put a link to this code down below. Hopefully you find that useful, and that's that.